So welcome back. We've already introduced one kind of a derivative for functions of more than one variable. And we've introduced, in the process of introducing this derivative, we've introduced what is called the del operator. And when the del operator operates on a scalar function, we obtain what is called the gradient. And the gradient is one kind of a higher dimensional derivative. Now, before we generalize this idea to fields, which could have vectorial character, for instance, the velocity field, if you were to measure the velocity field of a fluid in motion or of wind, or if you were to measure the electric field or the magnetic field, they are all vectors. And if they pervade all of space and you want to define this vector at each point in space and perhaps in time, you obtain what is called a vector field. Now, there is a generalization of the derivative also applicable to these kinds of vector fields. And again, we'll make use of the del operator. But before we get there, we need to explore a little bit further the vectorial nature of the del operator itself. And before we are able to do that, we need to first establish what do we mean by a vector in the first place. Now, the usual definition of a vector is something which has both a magnitude and a direction. And this suffices in so far as its geometrical interpretation is concerned. But let's say I give you something like a new vector. Let's say we were to construct, or let's use a different pen. Let's say I were to construct a vector, say, let's call that vector f, okay? And that contains as the x coordinates, as the number of perhaps apples we have in a basket and the number of oranges we have in a basket, right? I'm just trying to construct a vector and see if it indeed is a vector, right? So I have two components, the number of apples, A, and the number of oranges. Now, we could say that, okay, let's go to the coordinate system, Cartesian coordinate systems. We have the x-axis and the y-axis, and I'm going to plot the number of apples along the x-axis and number of oranges along the y-axis. And if I have A as a number of apples and O as a number of oranges, I could perhaps draw a vector in this manner, and that should constitute vector F. Let's say this is one of our baskets which contains A apples and O oranges, and maybe I'll use a subscript A1 and O1, and correspondingly we have a vector F1. So let's say that's basket 1. Now I have another basket F2 which has, say, A2 number of apples plus O2 number of oranges. So if we were to ask the question, what is the net vector? That'll be the total number of fruits, perhaps. So the total vector I can easily add, and I'll get F1 plus F2, which is the number of apples gets added, and the number of oranges also get added. So this looks fairly okay. This is the usual vector addition, which we are familiar with. So does it mean that if I have the number of apples as one component of a vector and number of oranges as the other component of a vector, that is a legitimate definition of a vector? Well, it turns out that this kind of a way of defining a vector, which has maybe two or multiple components, is not sufficient for us to have what we technically mean by a vector in the physical and mathematical sense of the word. In particular, a vector has to have some feature, some kind of a transformation, which will mix its components to give us a new component. For instance, supposing I were to, instead of using x and y as the coordinate system that we have right now, I were to rotate this coordinate system. So perhaps instead of having x, y depicted in this manner, I were to rotate the coordinate system and define new coordinate axis, say x bar and y bar. Maybe this makes an angle phi with the original coordinate system. Now, in this rotated coordinate system, do you think the vector f1 will have any of its components changed? No, right? Because f1 is just contains a number of apples. It doesn't matter what coordinate system in space we use to depict the number of apples or the number of oranges. So to put it simply, just because we have multiple components that we decide to arrange in the form of something which looks like a vector does not necessarily mean that it is a vector. And to be a little bit more precise, which leads to something of a circular definition, but that's the nature of things. That's just the nature of things. A vector, in the mathematical sense that we use it, and that's how we use it in most applications, is something which has right transformation properties. A vector is something which has the right transformation properties. Right transformation properties. And in many ways, a vector is defined by the way it gets transformed under coordinate transformations. And one of the most standard coordinate transformations based on which we define vectors is the rotation of the underlying coordinate system. So the very, very typical, the most characteristic example of a vector is just the position vector, or perhaps even the velocity vector. So let me give you an example of how that works out. And then we'll, in the next module, we're going to build this and we're going to test explicitly if the del operator that we have introduced, when it operates on a scalar field, and our claim was that that new thing, the new vector that we get, is indeed a vector. In order to really establish this fact, we need to make sure that the vector that we've constructed, which is the gradient vector, has the right transformation properties. So let's quickly review, and I'm sure you have had you've looked at this before. Let's see what happens to a typical vector, say the velocity vector. Let's take velocity as an example. You could also use position or any vector that you have in mind. Let's see what happens to the velocity vector, which has, say, two components, Vx along I plus Vy along j, in the original coordinate system, which is when you have the x and y coordinate system. What happens to this vector if I were to express it in terms of the new coordinate system, which I'm denoting by x bar and y bar? Now, if you just look at the geometrical picture in the original coordinate axis like this, perhaps this was making an angle theta. This is what we mean by Vx, and this vertical line is what we mean by Vy. And in the new coordinate system, maybe I should use this color. And in the new coordinate system, which is the x bar and y bar, I can drop a perpendicular like this. And it's this length, which will be Vx bar. And it's this height, which will be Vy bar. Now, how do I express Vy bar and Vx bar in terms of the original components, Vx and Vy? You can carry out the entire derivation just using this geometrical picture by using triangles as your underlying geometrical elements. If you already are familiar with this, you will recognize this as what is called the rotation matrix. I'm just going to do the calculation anyway using a very, very simple step-by-step approach. So let's look at this particular, we want to figure out these components, right? The green line, and this line, which I'm now overwritten with a white line. So we want to figure out what is this length and what is this length, right? And we already have this length. Okay, so if this angle is phi and the vector, the original vector made an angle theta with the original x-axis, and let's say this angle is phi, we can calculate this height, right? So we know what Vx is, we know what the horizontal component is. So let me just call this as h1. So what is h1? Well, I can take the tangent of phi. Tangent of phi will be h1 divided by Vx, and therefore h1 is just Vx tan of phi. So that takes care of this particular length, right? And now I can even calculate this hypotenuse, which let me just label that as AB. Okay, and this AB length would give me a part of the new Vx bar component, right? And the remaining part is this tiny length here. Okay, so what is this AB? Well, I can write cosine of phi, and cosine of phi is the base Vx divided by AB. So that's Vx by AB, and therefore AB is Vx divided by cosine of phi. Okay, now we know this h1. Maybe if you want, I can just draw this figure again. So we have this new coordinate system here, then we have our vector here. We have this length, and this angle is phi, and this original angle is theta. Okay, so we are calling this as AB. Let me label this as C. This height we know is h1, and we've already figured out what this is, right? Now, what is this height? Now we already know that this total height is Vy. So this height, maybe I can use a symbol P here, PB. This height PB is nothing but Vy, the original y component, Vy minus h1. Okay, so we have this, we have this. Now let's figure out what this is. Okay, Now, this angle is phi. This is 90 degree. So this is 90 minus phi. Therefore, this is 90 minus phi. Therefore, this angle is also phi. Okay. Given that this angle is phi, we know this particular length, we know PB. So we can figure out what BC is, right? So what is BC? Well, sine of phi is BC divided by the hypotenuse, which is PB, and that we figured out is Vy minus H1, and H1 we know is Vx tan phi. And so this gives us BC. So the total length AC, which is Vx bar, right? So let me just write down AC. AC is Vx bar is AB plus BC. We know AB is Vx by cosine phi. And we know BC is, if I take it on the other side, is Vy minus Vx tan phi times sine of phi. Now we have a Vx here, we have a Vx here. I can combine these two terms. This looks like Vx, and if you recall, tan of phi is sine of phi divided by cosine of phi. So therefore they share the common denominator cosine phi. So we have Vx divided by cosine of phi, and we have 1 minus sine square phi. Plus we have this component, which is Vy sine phi. Now 1 minus sine square phi is nothing but cosine square phi. So a cosine square phi cancels one of the cosine phi's in the denominator. And overall, we have the expression that Vx bar is Vx cosine phi plus Vy sine phi. So that's the new x component, or rather the x component of the same vector in the rotated coordinate system, right? In the same way, we can find out the y coordinate, which will be this length PC, and all we have to do is we can take if I want to calculate PC, I can just take the cosine of the angle phi, right? So if I write cosine of phi, that's just equal to cosine phi is base, which is this height, which is what we're interested in, Vy bar divided by P of B. That's Vy bar divided by P of B. And P of B, we already know, is Vy minus H1. Therefore, Vy bar is cosine phi Vy minus H1. And H1 we already figured out earlier is Vx tangent of phi. So that's Vx tangent of phi. And just multiplying the terms out, we find that this is minus Vx tangent phi is sine phi divided by cosine phi. So the cosine phi just cancels out. So it's minus Vx sine phi plus Vy cosine phi. And that's Vy bar. So the two new components of the vector, it's the same vector, but the underlying coordinate system has been rotated by an angle phi in the counterclockwise direction. So the two new coordinates, I can express it in the form of vector components. And the typical way of writing this is you can use Vx bar as one of the components of a vector, of a column vector, Vy bar as the other component, is equal to these four elements can be written in the form of matrix, and this matrix is what is called the rotation matrix. So I can have cosine phi here, sine phi here, minus sine phi, cosine phi. And when this matrix multiplies the original vector components, we end up obtaining the new vector components. And this is what is called the rotation matrix. Now notice one thing, that in the process of obtaining the new components, for instance, Vx bar or Vy bar, we took the original components and we have a mixing of these components. So Vx times cosine phi gets added to Vy times sine phi. And this is where the catch is. If I go back to how I was trying to define a vector based on the number of apples and oranges, if I were to rotate the coordinate system, and if I were to claim that the number of fruits is a vector in the new coordinate axis, that would give us one of the components as something which mixes the number of apples and the number of oranges. But that is something we all know is not allowed, right? So this might help us give some intuition as to what really constitutes a vector. any odd combination of components does not necessarily constitute a vector. For it to be a vector, it needs to transform in the right way. And given our understanding of what common vectors are, for instance, a position vector or a velocity vector, we postulate that if we were to define any new vector, it should respect the same kind of transformation properties as that of the position vector. And this is an example of a transformation property which allows us to test whether what we're defining as a vector is indeed a vector. If it is a vector, it should transform in the same way as this velocity vector transforms or a position vector transforms. So as a quick exercise before you watch the next video, try and think of a function of say two variables, a scalar function of two variables, and take its gradient and check whether this thing, which we called a new vector, the gradient vector, satisfies the same kind of transformation as what we just derived. In other words, if this field exists over coordinates x, y, and you were to calculate the gradient, and then you were to look at a new coordinate system, which is obtained from the original one by a rotation by an angle of phi, does the new gradient vector, or does the components of the gradient vector in the new coordinate system follow the same kind of a transformation using the similar rotation matrix that we just derived for a position or a velocity vector? So I hope this is making some sense. We'll build on this idea in the next video. Thanks for watching.